Alright, so this will be the last video for chapter 23, or Electrodynamics. In case I forgot to say this before, this chapter is called Electrodynamics because it's moving charges, right? As opposed to the last chapter, chapter 22, which was electrostatics, which was static, right? Non-moving charges. Okay, so now let's look at circuits. So circuit is any path which electrons can follow or move through, and again they move from the negative terminal to the positive terminal. So when you look at a circuit diagram, assume the switch here is closed, it'll show a current going from the positive terminal through the circuit and then into the negative terminal. And again, that's how we will describe currents, because currents are defined as positive charges moving. But we know in reality that it's the electrons that move. So in reality, electrons are coming from this end, the negative terminal, moving through, and then going into the positive terminal. Either way, the mathematics works the same. So there's two ways to connect a circuit, right? You can have a circuit that's in series, specifically the elements of the circuit are in series, or and essentially a series circuit is one where there's a single pathway that these electrons move through. So they all go through the same elements through the same pathway. And then there's parallel circuits, which form branches, essentially different paths that the electron can take. Maybe it'll go to this light bulb versus that light bulb, rather than both. So let's look at series circuits first. If you look at this image, you can get a better idea of what a series circuit is. Right here, all three of these light bulbs are connected in a row. So as electrons move from the battery, I guess really this way, they move from the battery, they'll go through light bulb A, then B, then C, and then back in. Right? If you think about it as the current, as a positive current, so current will come out through here, we'll go through A, B, and C, or however order, and then back into the battery. As opposed to, say, this parallel circuit here. This parallel circuit has different branches. So a current can go through this leg and back in, or it can go through this leg and back in, or it can go through that leg, right? So there's different options there. So we'll come back to that. The first series. Okay, so one single pathway. So when you look at a circuit in series, the resistors, the resistance of all the resistors add up. So a light bulb is really just a fancy resistor, right? A resistor is some circuit element that has a higher resistance than the wire itself. And generally resistors get hot because it's essentially just friction, right? A resistor has a higher density than the wire itself, so there's more collisions with the electrons or the current moving through, and that causes the current to drop, right? Less charge to move through per second. So a light bulb is just a resistor that emits heat in the form of visible light. Right, so some other resistor maybe emits heat in infrared, right, which we can't see, but light bulbs emit heat in the visible spectrum. So just think of light bulbs as resistors. Was the point of that? So when you have multiple resistors lined up in a circuit, you add up their total resistance. So say we had, let's see if we can use our paint or whiteboard. Alright, so say we have a 12-volt battery, and say this 12-volt battery, so let's draw a quick circuit. It's working a lot better than I thought it would. There we go. So these two lines here, the long and the shorter line, represent a battery, right? This is our positive end, and this is our negative end. And this here is our resistor. So say we have a resistor with, let's give it 2 ohms of resistance. An ohm is the unit of resistance, and it's given by this, and we represent it with this Greek letter. It's like in a horseshoe, capital omega. So let's say our resistor is 2 ohms. If we provide a circuit, this circuit with 12 volts, or a 12 volt battery, and it has one single light bulb resistor of 2 ohms, then we're going to have a current of 6 amps, right? 6 times 2 gives us 12. Not too bad. Now, if instead we replace that resistor with a 4 ohm resistor, right, instead of this 2 ohm one, then what does the current become? Well, it's got to drop to 3 amps, right? We doubled the resistance, and therefore we're going to have the current. Great. But now let's look at a system where we have 2 resistors. All right, so here we have two 2 ohm resistors in series, right? They're part of a single pathway. So the question is, what is our total resistance of our circuit? And bear with me here with my writing. This is not the best. But so 2 resistors in series, you add up those resistances, right? So 2 plus 2, of course, gives us 4 ohms. That means the total resistance of our circuit here is 4 ohms. And if the total resistance is 4 ohms, then as we saw previously, our 12 volts would give us 3 amps, right? In other words, 12 divided by 4 is 3. Ooh, it's not a great 3. Right, now if I added, say, a third resistor in series here, right, try to draw a zigzag, so now there's a third resistor in this circuit of ours, also 2 ohms, whew. Then now we have 12 volts. What is the total resistance now? So 2 plus 2 plus 2, so our total resistance now is 6 ohms, and so if we provide 12 volts, we know that if we provide 12 volts to a 6 ohm circuit, we know we'll get 2 amps, right? 12 divided by 6 gives us 2 amps. Wonderful. So what we find is that circuits in series, the more resistors you add, the higher the resistance, since you just add them directly, right? If I add another resistor, right? Let's say this one is a different ohmage. Let's give it. Ooh, that was bad. Let's say that this one is 1 ohm. So now my total resistance is 1 plus 2 plus 2 plus 2, so 7 ohms, right? If this bottom one happened to be a larger resistor, let's say 8 ohms, then now we got 8 plus 2, that's 10, plus 2 is 12, plus 1 is 13. So you just add them up, and the higher the resistance, the lower the current. So again, series circuits, you add the resistors straight. The more resistors you have, the higher the total resistance. The higher the total resistance, the lower the current. If we jump back to the slide, let's look at part 3, or step 3. So current is equal to voltage supplied by the source divided by the total resistance in the circuit. So that's just Ohm's law, right? Current is voltage divided by resistance. 4. The total voltage impressed across a series circuit divides among the individual electrical devices in the circuit, so that the sum of the voltage drops across the resistance of each individual device is equal to the total voltage supplied by the source. So let's jump back to our board for this. So if we look back at our 2 resistor circuit, let's try to understand what that statement 4 said. So the total voltage impressed across a series circuit divides among the individual electrical devices in the circuit. So essentially, we have a 12 volt drop here, right? The current comes out at the positive 12 end and goes back into the battery at the 0 volt end. So the charges aren't gonna re-enter the battery until they've gone through that 12-volt drop, right? Think of it as like a ball having to fall through some length of or some height in order to reach the ground. So first thing, we ignore the resistance in the wire. Now, in reality, wires have resistance, but they're super, super tiny, so we can ignore them in comparison to actual resistors and light bulbs. So we assume there's no voltage drop across the wire. The voltage drop only occurs at the resistors. So here, we'll have a voltage drop of 6 volts and a voltage drop of 6 volts here, because that adds up to 12. So keep in mind that this is a voltage drop. It's not the voltage provided by these resistors. These resistors are not batteries. Ooh, that's supposed to be a triangle for change. These resistors are not batteries. So when the current goes through the wire, it doesn't have any drop, and the current has to get back to 0 volts to go back to get into the battery. So 0 voltage drop, then it hits this resistor. It goes across 6 volts here, and then it goes across 6 volts on the second one. 6 plus 6 is 12, so now we're at 0. If instead we had, let's say, 3 resistors, and again, all 2 ohms. What matters here is they're all the same resistance. Then the drop across each resistor will be 4. Ooh, that was a bad 4. Will be 4 volts. Again, so that once you make it through all of them, you make it all the way through. You've dropped through 12 volts, right? If we had 4 resistors, then we would have a drop of 3 volts each. That way they add up to the 12. Alright, so looking back here, number 5, the voltage drop across each device are proportional to its resistance. So the voltage drop actually depends on what the resistors are. So here we said that all the resistors were the same resistance. But what if we said they weren't all the same resistance? So what if this one was 2 ohms, and this one here we said was 1 ohm, right? So now we're going to have a bigger voltage drop across the 2 ohm one. So the voltage drop here would be 8 volts, and the voltage drop here would be 4, right? Again, we see that as you make it through, 8 plus 4 is 12, so we're back to 0 volts, and we get to the battery. If it helps, you can think of these as negative, right? They're opposite. So the voltage drops as we go through here. We go negative. We start at 12, then we lose 8, so we're at 4, and then we lose 4, so we're at 0, and we come back in. I'm not going to have you guys figure out any sort of math with these. It's all proportionality. But what we see is that Ohm's law follows for each of these resistors, right? If we have an 8-volt drop here, we get 8 volts equals 2 ohms, and that must mean that our current is 4 amps, right? Here we have 4 volts equal to 1 ohm, and of course we need to have the same current since it's one pathway, and 4 amps equals our current. If we add up the total resistors, we'll see that we get 3 ohms of total resistance. So 12 divided by 3 gives us 4 amps. Alright, so we have one more point to make. And then with series circuits, if one device fails, the current in the entire circuit ceases. So if one of these resistors breaks, if one of these light bulbs breaks, the entire circuit is out. So Christmas lights set up in series are not very great, because if you lose one bulb, all the bulbs go out. Everything goes out that's in that circuit, because we now have basically a hole in our circuit. Okay, so next we have parallel circuits, and we'll look at that in the next video.